Hi everyone, this is Nicole Bernucci, and what I'm going to do today is introduce our new topic, which is Newton's laws. So this whole time we've been looking at kinematics before we moved from Newton's laws here, and we looked at how to model motion. So we've never asked the question of why things move during this entire time. So Newton's laws describe the why of things moving, and of course what we can do with Newton's laws is if we know why things are moving, we can predict how things move. So once again, we're going to analyze motion, but we're going to do it through the idea of forces. So the big idea is how do we model motion, and how do we know why things move? So before we go into the applications, we're going to start talking about Newton's basic laws. Many of you know these laws already, but I'm just going to give some applications. And although I'm going to introduce them now, I'm going to actually extend those applications throughout the year. So even though, like I said, I'm going to say Newton's first law, you'll hear me say it many times, and over time you'll learn the applications of these laws. So the first law, Newton's first law, is objects in motion stay in motion, objects at rest stay at rest unless acted upon by an outside force. So I'll describe that application. Newton's second law, let me come back to that really quickly. I'll describe that application in terms of these concepts called inertia and mass. So I'll give you some examples of that and describe why it's hard to move something heavy, right? I think we all have that experience, but Newton's laws describe that. Also, why is it hard to stop something moving once it's already moving? Again, this relates to its object's mass and its inertia, so I'll be defining those ideas. Now coming to Newton's second law, it's not a famous saying for Newton's second law because it's essentially a relationship between the mass and acceleration and force. So Newton's second law is F equals ma, mostly, and we're going to actually spend a lot of time on Newton's second law because if we know the net forces on the system, the sum of all the forces, we can understand what the object's doing. And there are many applications of that, so we're going to spend a lot of time on that. But one really quick relationship I'm going to discuss in the video is object's weight, the difference between weight and mass. And lastly, the last thing that I'll cover today in this video is Newton's third law. So Newton's law says for every action there's an equal opposite reaction. So if we tie in Newton's second law, we can describe why things do what they do. For example, I'll talk about a gun recoil and what happens when a bug hits a windshield. So we can actually describe why we see what happens using Newton's third law. Although I'm not going to cover friction here, but in the next couple classes I will cover friction and its applications. So a combination of these three laws will describe why things move. And I'll give you an example of application of all three laws to see why it actually does describe motion. So, there's a little video, or a little sound clip there. So, first let's talk about Newton's first law, and like I said, you know this already, but let's dissect this law. Let's figure out what it actually means, because just saying this, I don't think is helpful. So, just because it's here, I'm going to say it. So, objects in motion stay in motion. So, what this means, really, is that objects keep their motion. If it's moving, it stays moving. If an object is moving at a zero velocity, so at rest, it stays at that velocity. So even though this is technically a separate part, objects at rest stay at rest, it's really a continuation of the first part because really it says that if an object has motion, it's going to keep its constant motion. So the second part, unless there's an outside force, that kind of describes the everything else case, right? So if there is a force, a net force on the system, let's be careful with that. If there is a net force, so an unbalanced force, then the object will change its motion. And that's a really big way to say what's going on here. So let's go ahead and write these down as notes. So give me one quick second here as I open up the program to write notes. Sorry about this. It should be under workspace. It should be under e-instruction. Yes, this is super helpful for you, I know. Device manager. Sorry about this. Things I should have ready. Don't mind me. Here we go. Workspace. There we go. Okay, sorry, I know there was a quick little pause there. I just wanted to get my notes So let's just, take a look at this and dissect this a little more, like I said. So basically, Newton's first law of motion says that objects will keep their motion. So objects will keep their motion unless there is, and the key word here is an unbalanced force. Sorry about the spelling. Unless there's an unbalanced force in which the object will change its motion. And notice that anytime we change its motion, that's by definition acceleration. So, and an unbalanced force or a net force. So I'm just going to quickly define what a net force is, or unbalanced force is, for example, if I push this object down with 10 newtons of force, and push this object with 10 newtons upward, we'll find that it's essentially the net force of this system is the sum of the forces. But what happens is my up force will cancel out some of my down force, right? If I push up and down with the same amount, it would be like nothing's moving at all. So here's a case when we have a net force of 0, but notice that the forces here are balanced because the values are the same. They're just opposite directions. So this is a balanced force. So this comes back to this part right here. So if we have a balanced force, so balanced forces keep their motion. And just like a quick couple of examples of what this means, actually this can model a case like if you have like a coffee, cup of coffee on a table, right? Well, as we'll learn, gravity's acting on this object, which is always the case, like this. So we'll have the force of gravity acting down. But we see that the object doesn't keep falling, right? There must be something there. So we call this the normal force, which comes from the table. So the table pushes up, gravity pushes down. Now the table's pretty smart. It will actually push as much as gravity pulls down. So using those numbers again, say gravity pulls down with 10, the table will push up with 10. So how do I know? Because the object doesn't move. There's a balanced force system. This explains why this is the case. So a coffee cup at rest basically is Newton's first law. An object at rest will stay at rest. That's because there is a balanced force system. And extending this into physics, the acceleration of the system or the change in motion 0. That's because we are at rest. So I hope you can see how all this is connected. But if I have another case, say I'm now pushing the coffee mug. So let's take the coffee mug, but now my hand's on it, and I'm pushing the coffee mug with some applied force like this. So we could still have gravity and the table act on this, right? Because as long as it's on the table, these are going to, and it's gravity, which is always the case. But notice that these forces will cancel out. But this one will not. This is unbalanced. Which means that we have a non-zero net force. So what I mean by non-zero is this is, if I make up a number as 5 newtons. So when you have a non-zero net force, this object will change its motion. So in other words, this will accelerate. And again, it's non-zero, just meaning that it's, not zero, it can be any number. And Newton's second law basically says that the amount that this object accelerates depends on the mass, so F equals ma like this. So if I have the net force and the mass, I could find its acceleration. Pretty powerful, right? It describes all motion, why things move. pretty amazing. We're going to spend a lot of class time talking about all different models of systems and how they're going to move based on analyzing the forces on the system. So a big chunk of this lecture, as I continue it, will be how do we analyze these forces, etc. like that. So let's go back to our PowerPoint, and the music came back on. So silly. Okay, so I kind of wrote these all in words as well. So you do not need a force to keep an object moving, which is weird, right? So, you know, the whole time when I'm talking about projectile motion, I say once it leaves the hand, it's only under influence of gravity, which is still true here. So, in other words, I could take an object and I could throw it. Now, once it leaves my hand, the force of my hand is gone. So the question is, how is it still moving? And the answer is Newton's first law, and objects in motion will stay moving. That means when you take your foot off the gas on the car, your car will continue moving. We know that. We have that experience. But imagine if that weren't true. If Newton's law wasn't true, if you take your foot off the gas, then your car will come to a complete stop, which would be pretty, you know, pretty interesting, right, in driving. Or if you stop pedaling with your bicycle, you would come to a complete stop. But we don't see that. We see that if we take, you know, we stop pedaling on a bicycle, that bicycle will actually keep going. It keeps its motion. So we do not need a force to keep an object moving. However, we do need a force to change an object's motion. So if I want to stop an object, I need a force. If I want to start an object moving, I need a force. And if I want to change the direction of an object, I need a force. All of those are all examples of acceleration, right? Slowing down, speeding up, changing direction. All these require a force. Now, the ability to keep an object in motion is dependent on an object's inertia, which is how big an object is. So it's dependent on its mass. So literally how much stuff the object's made out of, a collection of atoms. So that counts. That's mass. So for example, you know, just to give two examples, a pebble will have a little inertia, or a boulder will have a big inertia, because if you try to accelerate a pebble, it's pretty easy. You can give it a small force and it's going to move. But if you apply that same force to a boulder, it's not going to happen. Just because it's going to resist that change of motion because it's much bigger. So how easily affected objects are at forces depends on an object's mass. Again, you know this. If you take a shopping cart and you fill it up and you start running with, you know, you try to start that shopping cart, it's going to be hard. But once it's moving, you don't need a lot of force to keep it moving. But if you try to stop that shopping cart, it's going to be hard because you're changing that object's motion. So once again, based on an object's mass, the inertia that object has is affected. So we change an object's inertia when we go shopping. And the more inertia, the harder it is to change motion. You can, it just takes more force to do that. So the forces on the system is zero, the object will maintain constant motion, we said it already, and if the sum of the forces are not zero, then object will accelerate, so we said that. So, applications of Newton's first law, so sorry person, not trying to be mean here, but it's important to wear seatbelts for this, because when you're in your car, you feel your inertia. When you sit in your car, imagine yourself sitting in your car, and you press the gas, right? You go back into the car like this. So what's happening is that your body has inertia. It wants to stay doing what it's doing. When you're sitting in a car at rest, your body wants to stay at rest. But the car is moving while you're at rest. So what's really happening is you're staying in place and the car is hitting you in the back. Now, obviously, I'm not modeling that because the object's not moving, but that's what's happening in your car. Now, you feel heavy when that happens because that's your inertia resisting that change. Same if you were to stop short here. So if you look at the car, both you and the car have motion. So if you stop short with the car, because the car is the object that's stopping, you don't stop with the car, because you need a force to stop. Your body would keep moving. So that's what's happening in this little diagram right here. The body is actually moving beyond this because of that reason. So seatbelts are important. And that's why you feel force too, is because you have to change your motion. So when you go from moving 25 miles per hour to 0, you feel it in your body. In fact, you do this, right? Because you're moving forward and the car has stopped. So there's your inertia. Many applications of inertia. So generally, this is a generalization here, football players, the linemen, the people that prevent people from moving are usually bigger people because you don't want them to move. You want to keep the other players at bay, etc. like that. So linebackers usually have high mass because you want to make sure they stay and keep their motion, which is at rest. Generally, your quarterback are smaller because you do want that person to change their motion. They have to run through players. They have to go back and forth. So as a quick example, if I was running in a forest versus my husband who's like twice the size as me, if we're both running in a forest and we both were to zigzag, my husband would have a harder time because his inertia would get in the way because his body doesn't want to change because of his mass. I would have an easier time because I have less mass in the system. Lots of cool demonstrations, so I'll either demonstrate these in class or play these videos, but mostly what you'll see here is that an object at rest will stay at rest. So if we quickly look at this embroidery ring right here, a demonstration I do in class, I put a pen. You put it right above the bottle like this, and you take that ring out, there's no reason for this pen to move, so it will drop straight down. Now, there is an outside force, otherwise it would just stay there, but gravity still acts, and it will drop in a straight line and will actually go in. Same thing here, if I remove this pan, object at rest will stay at rest, so that egg will actually stay there. If that were not true, the egg would go with the pan, but it doesn't. Excuse me. So what we'll see the egg actually fall straight down here. It's a pretty cool demo. And this is actually fake, spoilers. This was actually just created with visual effects, but the tablecloth kind of demonstrates that as well. So, in conclusion of Newton's first law, if there are no outside forces, in other words, the forces balance or they cancel out, then the object keeps its constant motion. So be careful, it keeps its constant motion. If there's an outside force, the forces don't cancel, then the object will change its motion. And then, if it does, we move on to Newton's second law. So the next video, we'll start investigating Newton's second law.